Hi, hello everyone. Welcome to another video of Beyond Feed. In this video, we gonna look how we will transform 2D images to 3D using DUST3R, and also, main importantly, we will localize the pixels or the defects that we have in bounding box to the 3D to plot in the 3D model. So let's get into the video. So as you could know that in last video we have trained the images with a UI of DUST3R, but in this video we're gonna look how we will do it in code. So let me open a new notebook file, and then yeah, it's open, and then change the runtime to GPU most importantly, and let me rename it to content 2. And most importantly, I would like to say you to connect the drive. Connecting drive is very important. It's been connecting. Yeah. Also, I would like to say that so as you could see in my drive file, I have cloned the Dust3R repository where here in last video I have the detailed view of these cloning techniques, and I have already been cloned this repository and saved in the collab, and after that I have put it into the drive. So in drive you can see the Dust3R here, and also in the repository they have given the code snippet to do it on Python. So in last video we have tested this model with the UI provided by them on Gradio, but in this video we're gonna use this Python code to, let's say, construct the 3D model. So let's go into the video and then look. Uh, Also, I have created a run.py here in which I have copied everything from here. I have copied everything from here in this run.py. So the first thing will be loading the parameters and loading the model. Here I have choose the visual transformer large base encoder with 512 dpt, and I have given also the path to the images. As you could see here, the path to images is available here on the 3D samples version 2. Again, in last video, if you would have watched last video, here is the images. And also I have given the link for the last video in the description. Please check it. And I'm loading the image file names and then loading image, and the inference was running, and the global alignment aligner will start running. This global aligner will align every images uh, and the point cloud, separate point clouds together, optimize it to make an one single point cloud structure. Also, we have losses, calculate the loss, and finally we get our parameters like focal length of the camera, the poses, and the point cloud in 3D, and camera's intrinsic parameters. Poses are the position and orientation, where it's the eccentric parameters, and then the confidence mask. So also we could extract these, save these results on the NumPy file, and then we gonna download it and visualize the results. So this is what we're gonna do now. So let's run the code as usual. Let's start from installing the libraries. So here I have pasted the pip install requirements.txt and open 3D. Let's install this, run this cell. Now let's keep installing the required libraries. Once it's installed, let's run this run.py. All right. So let's keep installing. Now I have pasted on my run.py command on next cell. Let's run this once the above installation completed. Yeah, perfect. It's completed. Now we're gonna run this cell as well. So the cell starts running. It take a few minutes. So it starts. It says that RO 2D is not found. So it's gonna use the slow Python version instead. So this is the basic warning that we get because we are using the PyTorch version CUDA. So now the model being already installed, and then yeah, now the model is being installed. Let's see. So it take a few moments. Let's wait for a few moments till the installation complete. And one more important thing is that in this run.py, I have also mentioned the path for saving your results. So if you go to the line number, yeah, on the line number 65, you can see in my 3D results 190725. So let's go to my drive directly, and then I go with DUST3R results 190. Here you could see I have like 1907. Now it's nothing. Once it finishes the task, it gonna save every results. So it's like 45%. The contents are loaded, and now it's 45%. Let's see. Let's wait for the results. Now you could see the program has been completed, and every parameters have been saved. Now let's go and look at the folder where we have given. Perfect. Now every parameters have been saved, and the main thing we need is the points in 3d.numpy. So this is the main thing we need. And let's download this. So it's keep downloading. Perfect. It's downloaded, and then we can save it in the folder. I mean, we created a project directory in local, and let's start visualizing, and then we localize the defect. So we have downloaded every parameters and been store the parameters in the project directory. We have also created a notebook file where we could evaluate the results. And then also we have the images, that is the 3D samples version 2. Let's go and look at let's open Visual Studio and see the results, and then map the defect or the 2D pixels on 3D. Let's go. We have opened our Visual Studio Code, and I have this notebook been already created and tested. And uh, please look at the description for this notebook. You will find it, and you can test it once you have the results. So I'm gonna run one by one, and So first cell is loading the model and then testing the testing the statistics of the results. So let's copy path and paste it here because last time I tested in different path. Now let's run this cell. Yeah, so the cells have been completed. Let's open in the text editor. So first you can see the intrinsic parameters for the 12 images that we have uploaded. You can see the shape that 12 comma 3 comma 3, that the H matrix that is 3 comma 3. And going further on the poses, you can see 12 comma 4 comma 4, the eccentric parameters that is 4 comma 4, and for 12 different images, and the focal loss as well for 12 comma 1, which is for focal loss for 12 images, and the confidence mask as well for also 12 images. So number of masks is 12, and the shape is the image shape that we resized for uh, constructing the image. So now let's go and visualize. Now we will construct the points 3D that we have saved. As you remember, we saved the PTS 3D.npy. So we're gonna use that points for example, let's say I'm gonna print this. Let's import the libraries and then the path and then the stats. So this gives the statistics of these points 3D. So let's say the shape of there is 12 images, let's say, and every sh- every image have the shape of the size of the image and 3. 3 is not the channel, but it's the 3D point like X, Y, Z, and the minimum coordinates is this. So this is the point cloud that we have, like the point cloud of like uh, inferred by the model. So once inference is done, this is the prediction. So basically in 2D, you get the prediction in, let's say, uh, H, H, W, and your channel C. But here it's like the same, but instead of C, you have Z, which is your 3D point. So X, Y, Z. Again, now you have the text editor, sorry, these values in the text editor. And now it's time to reconstruct this, structure this by removing some noises. Now I gonna run these. Let's say you need to pass the images as well. So I gonna give the path of the image here, and I gonna give the parameters directory, path for the parameters directory here. Now let's run this. So it's loading the data and loading and resizing, and image has been visualized. You can see a new window have been opened. This is the Open 3D, and let's go. Boom. Here we go. The visualization have been done clearly, and you can see the how the image has been reconstructed. It's a bit noisy, but since we are testing, we have tested with the less part of images. But if you give a lot of images, probably you're gonna get the perfect reconstructions. Here we go. So let's stop the running. You can stop just clicking here. Yeah, the kernel is being interpreting, so you can see. Yeah, so also the color have been the color also have been plotted on the point, but what I can say is now we can test with the gray image. So again, I need to restart and run every cells. So I've been running every cells. Now I can make the colors, every colors to grayscale. So now I have changed the colors to gray. I just uh, commented out the colors that we have implement to the 3D model. But now I have made every colors to grayscale. Let's visualize it now. And also here you can see that I have wrote a line to save the constructed point cloud in the folder. So the point cloud has been saved, as you could see here. Now what we could do is let's localize localize the 2D pixel in the saved 3D model. So this is what we're gonna do now. Let's play with it. So this one is I load the parameters and point cloud path that we have saved in previous cell, and you load it. Then you visualize in you read it in the Open 3D library. And here is my like just a random the pixel. Now what we're gonna do is that using the we calculate the center point. That let's consider this is a bounding box, and let's center uh, like we find the center of the bounding box, and then we map it on the 3D model. So for example, how is this done is from points 3D that we have generated on the inference of the DUST3R. So once DUST3R model, the visual transformer gives us the predictions, as you could see on the previous explanation that I have explained. Once we get that PTS 3D, you have every information per image and per pixels and per 3D points. So now we have this 2D pixels, and we directly, it's a straightforward method that we map these 2D pixels to 3D. So basically you find the 3D point where you want to plot it, and then you just need to directly map it. So let's run this, and you can see. So it's running, and oops, something happened. So let's rerun this. Yeah, now the results have been loaded. You can see here mm, the grayscale image. Yeah, perfect. So you can see the blue color have been marked, in which we have transformed our pixel here. So just in case you can see the marker here on this point where we have plotted the marker. So for example, let's visualize the pixel this place this location in 2D. Okay, so let's close this, and yeah, perfect. Now Let's do this in separate cell. So basically, I will make the path image sample image path. So I copy this copy path, and also I suggest you to use Copilot. So it will be very useful. For example, you can type a command. Let's say visualize the sample image with the resizing of, let's say the resized image was 512 comma 368. Just copy this and paste it on your comment. So let's say you have the suggestions. Let's just click uh, tab. So you get suggestion a lot. Now you have this, and yeah. So let's, and also I would add a red bounding box to the resized image. Yeah, perfect. So let's copy the bounding box here. 200, 200, 150, and 2020. So 2020 is there. Yeah, perfect. 200, 200. Yeah, perfect. Everything is cool. Copilot is working fine. And I think it's not plotted. Patch data. Oh, yeah, perfect. So I could verify that the bounding box have been plotted. And as you could see in the results, also the 3D point have been plotted. So in this case, in the real application, you can find the defect using some object detection algorithms. And once you get that, you use those images to reconstruct and then plot the defects in the defect location in 2D to 3D model, so that you can know that in which location the defect have been or the object have been uh, uh, addressed. So, for example, it will be used in many cases on, for example, one application that comes to my mind is that inspections. For example, you are inspecting a chase, let's say a chase of car or chase of motor vehicles. So, after the inspection of the welding, after once the welding is completed, the robotic welding is completed, it comes to the inspection part where you have the camera, and the camera goes through the chase, and once you have the images reconstructed, and the defect could be localized on the chase, or it could be used on the windmills for the inspections, and also solar panels for inspections, etc. So this is for this video. I hope you have enjoyed, and uh, please contact me for this notebook file, which is on the contact information will be on the descriptions. Thank you. Thank you for listening. We'll see you on next video. Bye bye.